So today we really pull it all together. We've looked at the partition function for the molecules, and we've gone through translation, rotation, all of that. Then we looked at equipartition, where we're at high enough temperature that those individual distinctions kind of blur, and we have the partition function, internal energy and entropy, just modeled with 3/2 nRT. Now we're going to go back to the statistics today, and we're going to look at 2 and 3 level systems, and we're going to actually calculate the energy, enthalpy, the Gibbs Free Energy, and equilibrium constant. So we're going to look at now the quantum roots of thermodynamics. So it's really kind of been building to today's lecture, so I'm glad you're here. And so this is the statistical part. We use that Boltzmann distribution to build up the partition function. And then once we have that partition function, that is the connection to all of thermodynamics. The internal energy, entropy, enthalpy, Helmholtz, and Gibbs free energies, and the heat capacities, and then the equilibrium constant. So we're going to cover all of this today, sort of a culminating activity. This entropy is described in terms of the number of states that are available at a given temperature. Well, that is the Boltzmann distribution, and that is that partition function. So this entropy defined as Boltzmann's constant times the natural log of W. This was the weighting factors of all of the microstates. And so he actually got into all of the permutations of the ways to put these systems together. We did not go into that in any depth, really. We could have, but it would have just taken many, many more lectures. We just really focused on the partition function. But yeah, this is his grave, and you see his equation up there. Entropy is K log W, and so it's a historical place. And so with that, let's do this calculation using a simple partition function and calculating all of these other equations. So this is a 3-level system, and this ties back to our conversion of energies over to temperatures. Remember we had, say, rotational energies, the rotational constant. We converted that to a rotational temperature. And then if we had a vibrational frequency, we converted that from wave numbers over to vibrational temperature. So this example uses the energy levels spaced in terms of temperature. Okay, so we have a 3-level system of non-degenerate energy levels. So that means that degeneracy is 1 for all 3. And that the spacing is equal to the value of kT at 25 Kelvin. So this would be the way you'd write out that 3-level system. The ground state, 25 Kelvin for the first spacing, and then another 25 Kelvin for the next spacing. So this is the 3-level system described by that text. And so that's, I guess, the most difficult part of these problems is getting started. As you read the text, and what is it telling you? How do you set up the system? I'm going to pause here just in case there's any wording that bugs you, and I can clarify. Could you have gotten the 3-level system from the text that you see? That's the question you should ask yourself. Okay, so let me back up a little bit and let's calculate that partition function. So we have those 3 levels. We have the definition of the partition function. Is this a countable number of levels? Yes, and so we're going to use the summation. And so we have the degeneracy. It's 1 for all 3 cases, so you don't see it in the calculation because it's just 1. The ground state's e to the 0 here. And then notice that calculate the molecular partition function at 25 Kelvin. So this is, I guess, the confusing part of the way I built this problem, and that is the temperature, the thermal temperature of the system is also 25 Kelvin. So that's coincidental. It didn't have to be 25 Kelvin. But I kind of wanted the math to work out in those exponents. I wanted it to be 25 divided by 25, which is 1, or 50 divided by 25, which is 2. So I just wanted it to be simple. So I went ahead and said T is equal to 25 Kelvin. And so in doing the partition function, we have e to the 0, then we have e to the 25 Kelvin here, the energy divided by the temperature, and 50, which is the energy level divided by the temperature. So that's e to the 1 and e to the minus 2. So you add all those together, you get 1.503. Is everybody confident that they could do that part? Okay. So now that we have the partition function, we can calculate the internal energy. So calculate the molar internal energy. Now this is something that I asked for molar internal energy, so we're going to be thinking in terms of joules per mole. So we have that partition function. This is the probability for state I. Remember that? So that's probability. And here's the energy for state I. And so you sum up for the expectation value the internal energy times the probability for each level. So there's 3 levels, so you have 3 parts to this calculation. And so here are the 3 parts. Here's the energy for the lowest state, the middle state, and the higher state. And notice I just stuck R in there. So R is 8.3145 joules per mole per Kelvin. And so when you multiply that by the temperature, you get the energy in joules per mole. Okay. And so then, this simplifies. I've done some algebra here. I pulled a 2 out of the 50, and so I have 2 times this factor here. And so this is our calculation. When you multiply all that together, you get 88.3 joules per mole. Okay. And again, if it's going pretty quick, that's okay. This is in the notes, so you can download it and you can go through it by hand. But we'll do an example after this. So that's 88.3 joules per mole for the internal energy. Now what's the entropy? Well, we have this equation. It's the internal energy divided by the temperature. Okay. And then the gas constant times ln Q. Now you might say, wait, I saw on a previous slide that we used K instead of R. Okay, you would use K if you were doing joules. So think about this. The Boltzmann's constant is equal to 1.38 times 10 to the negative 23, negative 23 joules per Kelvin. What if I multiplied that to get joules per mole by Avogadro's number? Like 6.022 times 10 to the 23rd mole minus 1, and it equals 8.314 joules per mole Kelvin. So R is Boltzmann's constant. You've been using it since your freshman year and didn't know that. Okay, so it's just if you look at the units, it's joules per Kelvin, but it's joules per mole Kelvin. So the per mole came in there by Avogadro's number. It's the same constant. Okay. Yeah, it's crazy. So you can use R instead of K. It just depends on what units you want. So R is just K converted to per mole. Okay, so we use R here instead of K. And then the partition function that we calculated previously. So this first piece was 3.5, the second piece was 3.4, so we end up with 6.92 joules per mole per Kelvin. So that's our entropy. Then we can calculate the enthalpy, U plus RT. So we have the internal energy and then R times the temperature of our system, and so we end up with 296 joules per mole. Notice that the R has per Kelvin in it, but we're multiplying by temperature, so this per Kelvin cancels with the Kelvin, and so we end up with joules per mole in terms of enthalpy. The Helmholtz energy is U minus TS, and so the internal energy minus the temperature times the entropy, and entropy has these units where the Kelvin and per Kelvin cancel, and so we end up with negative 84.7 joules per mole.
So once you get internal energy, it just kind of cascades down.
Yeah, exactly. And so then, it's very easy once you get U. Yeah. And then G is H minus TS. And so that's 123 joules per mole. So these are very simple calculations, but they take time, so you got to be pretty quick with it. You can't be sitting there going, what do I do next? Notice that the thing that required the most thought was the very beginning. You read the text, you've got to know what kind of system you're dealing with. Once you get that, then you can calculate the partition function, and then you're ready to go with it. So this is the summary of the results. These are all of our calculations, and that's why I talk about being a USHAG calculation as all 5 pieces, internal energy, entropy, etc. Now let's talk about the Gibbs energy a little bit. So for an ideal gas, we have A plus PV. We can do some substitutions. There are different thermodynamic equations for some of the same quantities. And so we're not really deriving them. We do have this supplemental on Stirling's approximation to get out of the number of particles factorial. So when we looked at this large Q, how do we describe this large Q? This is for what we call an ensemble. Not really a musical ensemble, but that's an E. Okay. So we've been dealing, like jumping back and forth between one particle and like a mole of particles. So there's an issue when you jump up to a large collection of molecules. That's called an ensemble. And so think about statistics. Now you're counting a large amount of molecules. And it matters if those molecules are identical or not. And our molecules are. I can't distinguish between one water molecule or another. Think about if you're rolling 5 die, okay? Does it matter which one you actually pick up first? Like if you roll 5 and you say, okay, I'm going to put them all in order, it doesn't matter which one you grab first. All it matters is what number they show. Okay? Same thing with molecules. When we roll the dice and they have different energies, it doesn't matter. I don't have labels on water molecules. I don't have a serial number for every water molecule. And so they're indistinguishable. And when they're indistinguishable, you end up having to divide that partition function so that you don't overcount. And so that's what this piece is. But look at this. This is n factorial, which is going to explode when we get to a mole. In fact, your calculator, you try to get up to 100 factorial, and it'll give you an error. And so we're way far away from being able to calculate the factorial of a mole. But Stirling's approximation allows us to break that piece out. Okay. Here we can take this this ratio. So the natural log of a ratio is the sum. And you change the sign, so it's a minus here. So this is a plus. So we have that n factorial here, and we can use Stirling's approximation to get rid of that n factorial. So this piece right here becomes this, and notice the factorial is gone. Okay. And so then I can recombine that. So some of the n's cancel and so on. And I can recombine that to where now this n comes out front. And I have Q over n. Now, number of molecules times K, I could make that nRT. I could have Avogadro's number times K, which gives it per mole, and then I can have the number of moles. And so nKT is the same as nRT. A little n, RT, so this is the number of moles. And if I have something multiplied by a log, that can also be used as an exponent. So here we have G is equal to this minus RT ln partition function over number of identical molecules or particles raised to the number of moles that I have. It took me a while to get to this point, but I wanted to take this piece now and look at the delta G for a reaction. So something familiar arises in this. You see that exponent that has the number of moles in it. So let's look at chemical equilibrium. We have A moles of molecule A plus B moles of molecule B gives us C and D with their numbers of moles. And so the delta G for this reaction is going to be products minus reactants. We'll develop that again in a couple of weeks in order to review. But whenever you're calculating delta H for reaction, delta S, delta G, you take the products and you subtract the reactants. And so you see the signs here. The products have positive signs and the reactants have negative signs. Everybody with me so far? Okay. Let's put in those delta G values. Those G values. So this GC is right here. Okay. That's this piece. And D and A and B. And notice the C is out front. Well, when I have C times that, it can be up here as an exponent. And so I have minus RT times these four things. And then, again, if it's the minus logs, they can be brought down as a fraction. And so then I have the products on top and the reactants on bottom. And that is the equilibrium constant. So the partition function and the math related to that gives us the products over the reactants inside the log. And that gives us the equilibrium constant expression. And then likewise, if we were to flip that around, the equilibrium constant is e to the minus delta G over RT. So this equilibrium constant is just an approximation of the partition functions. So this is an amazing result. I mean, I don't know that you're that excited about it, but I am. You get to this point and you're using statistics, and all of a sudden something you're very familiar with emerges. Like, how did we just solve for the equilibrium constant? By just playing with delta G's. And it's pretty incredible. So this I call miracle of miracles. Statistical treatment of quantized states explains the following observations. The heat capacity goes to zero as temperature goes to zero. That was one of the failures of classical physics. Entropy is a measure of the density of states at a given temperature. So how many states can I populate at a given temperature? That gives a more definite explanation of entropy than just saying it's a measure of disorder. Right? You've heard people say, "Oh, entropy is a measure of disorder." Well, how? How is it a measure of disorder? Well, now you have an answer for that. It's really just related to the number of states that can be populated at a given temperature. And so if I raise the temperature, I'm going to raise the entropy, and that's the observation that we have. Okay. If I have a reaction that goes from a liquid state to a gaseous state, that raises the entropy. Because you think about how many translational energies can now be populated. They're much closer together. So gases have much more entropy than liquids. And liquids have much more entropy than solids. The spontaneous change, this delta G is driven statistically. We can see that also with the equilibrium constant. So this equilibrium constant expression that you learned were just approximations of the partition function. So when we took the concentration, the aqueous concentration, and raised it to the power of the number of moles, we were approximating the partition function. We were looking at pressure in a system at equilibrium, raised to the number of moles, we were just approximating that partition function. And the pressure one especially is a very good approximation of the partition function, because the equal partition of those translational energy levels. Really all a gas can do is translate and rotate. And so let's take a Kahoot on this to kind of capture our learning, and then we can redo these calculations with a little different system by hand. So this will check your learning or your understanding of it. You trying to wake up? All right. The code is 110247. You already messed up your name?
No, I'll bring show the first one.
Okay.
I don't win at something.
There's no sticker for that.
I think you should get a sticker for that. 100%.
Maybe I'll bring some stickers for me. Well deserved. It's too early.
Okay, that looks like it's everybody that's here today. Man, I can't believe these people missed today. That's not a good thing. Okay. Pardon?
You record your lectures anyway.
Yeah, I know. They can't get stickers.
Fools.
That's right. Yeah.
They also can't get the games.
Yeah, that's true. So an endothermic reaction can't truly be spontaneous. True or false? We didn't really talk too much about spontaneity. Sorry. Such a...
What is truly?
I don't know, actually. What does that mean? Just to make you nervous. It's almost a 50-50. Oh, dear. We'll talk about spontaneity here. If you look at it, if the T delta S is higher than delta H, then it's the negative part, so it's going to be spontaneous. So here's the delta G. Just think about it. The real question is, can delta S be positive or negative? Oh man, about a 50-50 split. No, not quite. So delta S can be negative, and so that can flip the sign. So it can be larger, yeah. All right, in this system, which is the most populated energy level at room temperature? So this is the system we just covered. Which one of those was the most populated at room temperature? Some slow clicks. Yay. Okay, very good. So if there's no degeneracy, it's pretty easy to say that the ground state, the lowest state, is most populated. These energy levels are pretty close together, though, and so it wouldn't be most populated by much. So it would be about 33% on each. Maybe it'd be 34% on the ground state. So it would be very close because the energy levels are close together, but still with the little mouse is on there. Last question. Equilibrium constant expressions use a to the a, so the species raised to the exponent, which are approximations of what? This is really the main question of the Kahoot that I was interested in. Very good. They're approximations of the partition function. And the reason our equilibrium constants may not be exactly right that we calculate by theory is that we're making approximations on our determination of the partition function. It'd be very hard to get an accurate computational calculation of an ion in water. So you think about all of the effects. You've got an ion surrounded by a cage of water molecules and all of the Coulombic charges and so on, and then it gets super complicated. You're not just dealing with a single species in space. The gas phase equilibrium constants, though, we can do pretty well.
Yeah, is there like a way to measure like quarks?
Measure quarks?
Yeah.
Not sure. Yeah. I mean, all I know is that they determine those with these super colliders. So the high energy physics, it sounds like I'm insulting them, but I'm not really. It's like you take a Swiss watch and throw it against the wall and pick through the parts to see how it works. So you're smashing the atom and seeing what flies out, and then saying, okay, at this energy we got these particles, and so then they crank up the energy and get more different types of particles fly out. What happens is then they'll convert back down to the lower energy forms, and so they'll see that this particle then is made up of these two or goes to those two, and so the tracks are amazing. They're not just particles flying out. It's in a magnetic field, so they'll turn in the magnetic field, which tells you what their charge is, and it's quite amazing.
So could something like smaller than an electron could go faster than the speed of light?
No, the speed of light in a vacuum seems to be the speed limit of the universe, okay, after the initial expansion. But you can get things to go faster than the speed of light in the medium. So, like the speed of light through glass is less than the speed of light in a vacuum. And then you can get, say, a particle to fly through that medium faster than the speed of light in that medium. See what I mean? Mm-hmm. Yeah. And so that's what's going on with some of the radiation detectors, is that these alpha particles and so on come out of the nucleus going a little bit faster than the speed of light in that medium. And so as they slow down, they emit radiation. And we can detect that radiation. So that's one way of detecting radioactive nuclei, is to look at this. And I've lost the name of that radiation effect, but that's what's going on with some of these scintillation detectors. Yeah.
I'm curious, because you said if they like smash the atom apart or whatnot, I was wondering like how fast they would have to go if they just like superheated or what.
Yeah, I don't know too much about it. Yeah. I'm reading a book. Well, I've got a book. I haven't started it yet on the Higgs boson and on mass. So I've got 2 books. One of the best authors that I've come across is Jim Baggott, Baggott. He publishes through Oxford University Press, and he's a popular science writer, but he does treat the science really well. So the things that I've read in this one called Quantum Story, the stuff I know about, he's gotten exactly correct as far as I can tell, you know. And so then the stuff that he's telling me that I don't know about, I trust, because I've seen, you know, sort of verified. He knows what he's talking about in terms of the quantum mechanics that we cover in this course, but I'm not a theoretical physicist. So he leaves me behind eventually, but I'm learning from him on those things, and I think he's a trustworthy author. But yet he writes it for, I say he's a popular author. I mean, he's writing it for, say, chemistry majors to learn about physics, right? Or people that have a science background that can understand and aren't intimidated by the vocabulary. But it's not like a textbook on physics. It's really telling the story of all the different scientists and how they made these discoveries. So let's look at some conceptual examples. Now that sort of the Kahoot primed our thinking about spontaneity and so on, let's think about this. So responses to heat. If we heat up a system, this one's obvious. If we heat up a system, we populate more energy levels. But what about responses to pressure? So what if we squeeze a system? Think about just the particle in a box, right? If we shrink the box, the energy level spacing increases. So we see this pressure effect as well. So if you squeeze a system, the energy levels in general will respond, and you get a lower partition function. We talk about the density of states. So in a given energy range, how many states are there? And so we can look at reactants and products and talk about, or at least in our mind, think about the density of states. So if I have a liquid, it's going to have a certain density of states. If then the product is all gas, it's going to have a higher density of states. Meaning in a given energy range, there's a 1,000 more translational energy levels than there would be, say, in a liquid. So this can lead to some interesting effects. Notice that reactants and products don't really have labels on them. When something comes to equilibrium, it's just the energy levels. And if your products happen to have a higher energy than the reactants, they're going to have fewer populations. So look at this. There's no way for the mathematics or the statistics to know that when going from this energy level to that energy level, I've gone from a reactant to a product. Right? Statistically, it's just rolling the dice. And so the Boltzmann factor calculation is just going to go fluidly from calculating the population of a product energy level and the calculation of a reactant energy level. So notice these bars here. You know, these bars, the ground state's the biggest bar, so it's most populated. But when you get here, this one is this wide, and then the very next level happens to be a product level. And so it's that wide. And then this one's a little smaller than that one, and this one's a little smaller. You see how it's just jumping from reactant to product statistically? And so then you look it up and you can say, all right, well, if I add up these are my product molecules, these are all my reactant molecules. The equilibrium lies on the reactant side. I have more reactants than products. So the ratio of products to reactants will be much less than 1. Make sense? Yeah, it's just statistics. Now, there's more to it than statistics. The molecules actually have to hit each other, but that's kinetics. We're talking about once it achieves equilibrium. It may, in our lifetime, never achieve equilibrium. I've got keys in my pocket. It's spontaneous for those to turn into rust or some sort of metal oxide, but that's kinetics. So this key is not at equilibrium with the oxygen on Earth's atmosphere. Okay, it will eventually, given enough eons, reach equilibrium with the oxygen in Earth's atmosphere and become, mostly products, metal oxide. Okay. So it may take a long time to reach equilibrium, but once you reach equilibrium, this would be what you'd have: products over reactants. Yes.
So if one set, like products or reactants, all levels were higher than the other, would that be like determining a spontaneous or not?
Yeah, so if we had a higher density of states of products, then we could put a whole lot more products, and when we do the ratio, then it would be forward driven. So let's look at this example. So now the density of states in our products is so close together that I get a lot of statistical population of my product levels and very little in my reactant levels. So this bar is, the ground state's still the most populated, but then this is the next one, and then the next one, the next one. So all of these are product levels, and then we get back to a reactant level, and then more product levels, and then a reactant, and more product. And then when I add up the probabilities, these are my products, and these are my reactants. And I've got a reaction now that lies to the right. If I were to draw it out, I'd have more products than reactants. I'd have a K greater than 1. And so this would be spontaneous in the forward direction. If I just mix the reactants together and let it go, it would form products and products and products, and then reach equilibrium where I have a lot more product than I have reactant. And so this is a way then to get, and not only that, but what's the average energy of the products? If we added up just the internal energy here, it would be, up here somewhere. And the energy of the reactants, these really don't change things much, so it's mostly the ground state energy. And so this is endothermic. It's uphill in internal energy and uphill in enthalpy, but yet it's spontaneous because the entropy change is so great. Okay. How do I know the entropy is higher for my products? Look at the number of levels that are populated. So I have a much higher entropy in my products than I do in my reactants, because I have many more energy levels populated. This, when we talk about measure of disorder, you see I have lots of options here. I like to think of disorder as options. Okay. Right? And so the products have a lot more options for which energy level those molecules can be in. The reactants, you really only have 3. Yes?
Can you say again how to tell if it's endothermic or
Just looking at this difference here. And so this difference here, we've got reactants going to products, it's uphill. And so when we plot the energy levels, that's really the internal energy that we're plotting. And then if we look at the enthalpy, it's related to that internal energy as well. So this would be endothermic, yet it would still be spontaneous because S is so big. So this would be greater than 0. And this would be greater than 0. But notice this minus sign right here. So T delta S would be a positive number, but we subtract that. And it overwhelms the endothermic nature of this reaction and gives us a negative delta G. So you always have this competition between enthalpy and entropy.
With that, so since all the statistics are on the reactants, that's exothermic.
It would still be endothermic because we're going uphill to the products. But yet the delta S would be negative. So in this case, this would be greater than 0. And it looks like I have more options in my reactants. And so I'm going to go ahead and say that the entropy is less than 0. Meaning when I go from reactants to products, I have fewer options. And so I've decreased my entropy. And so then this negative entropy cancels that negative sign, and so we have a doubly positive delta G. Right? It's positive because we have an endothermic reaction, and it's also positive because we have a negative entropy change. And so it's not going to be spontaneous. That doesn't mean you won't get some products, but it's overwhelmingly going to be weighted on the reactants. So if you started with all reactants, it's going to go forward a little bit, but not much.
That'd be your key, right? Same idea.
What do you mean the key?
Because like you said, it won't reach equilibrium with oxygen because it's not making a ton of iron oxide. So it's making a little bit of product with oxygen in the air, but not a ton.
No, that would be if it comes to equilibrium. I'm talking about the key would just be kinetics. It wants to go that direction, but the surface is once it forms an oxide layer, then it's kind of protected. It stops the reaction,
Okay.
and so it's access to the new metal. If you scrape it, then you're creating more access, and it will oxidize immediately. In fact, aluminum is so exothermic in its reaction with oxide and so oxygen and so spontaneous, you've probably never actually seen the true surface of aluminum. You think you have, but as soon as you scrape it, oxygen attacks. Now you've got, you can see through that oxide layer. It's pretty thin, and so it's still shiny, but aluminum oxidizes so fast that you probably haven't seen it. Would mirrors, aluminum mirrors are very, very reflective, but they still have an oxide layer on them. Yeah.
So would this be like a point of like protecting groups and organic? So
Yes.
want to like keep the product.
Yeah, absolutely.
equilibrium?
Yes, absolutely. And so we deal with kinetics a lot, even though we're not really doing kinetics calculations. A protecting group would stop a reaction at a particular place on a molecule. And in metals, that protective layer is an oxide layer. They call it a passivating layer. So it makes the surface passive. It wants to react with oxygen, but you're passivating it. Let's quickly do this, though, so we don't run out of time. This is our... Okay, so there's 5 here, so share one. Share one. You're going to get one from that, Dave.
I just. I'm not pressed.
Do I have one? Okay. Okay, great. So here the system's given to you as reactants and products, so A and B. We have A as a 3-level system. Now our energy is in wave numbers. So since we're seeing our energy in wave numbers, what form of Boltzmann's constant are we going to use? So mentally just think, okay, whenever I'm doing my Boltzmann factors, what Boltzmann constant are we going to use?
It's like KT. Centimeters over centimeters in Kelvin.
Yeah, so but what number would be like the 0.695?
Yeah.
Yeah, instead of 1.38 times 10 to the minus 38 joules per Kelvin, which I've seen students that come show me their work, or I'll see it in the work online. They'll convert everything to joules, and they'll have all these exponents everywhere, and just try to make life easier for yourself. Somewhat it may be satisfying to work in joules because you're comfortable with joules, but if the energy levels are in wave numbers, go ahead and work in wave numbers. Convert Boltzmann's constant to wave numbers, and then just work with your wave number energies. I'm going to sit and go through this problem with you. We want to calculate both the Boltzmann factors and the probabilities for both the reactants and the products. And so let's have somebody go through, let's label these energy levels 0, 1, and 2. Just so it matches the numbers on my sheet, I'm going to call it 0, 1, and 2 here. Okay? So can I have 6 volunteers? Because let's go quickly and calculate the Boltzmann factors. There's 6 of them to calculate. And so if I can just get one person to do one of the 6, it'd be great. So 6 volunteers. So you tell me which one you're going to do. Will you do one?
Yeah.
Okay. Would you do this one here? Okay, so Jared, you do this one. Okay. Yeah, and then somebody else calculate this one. Okay, Ian. So we got that one calculated. Someone else calculate this one. Who? Just want to make sure it's covered.
Sure.
Okay, you do that one. All right. And then, Alex, can you do this one?
For the B factors?
Yeah, the Boltzmann factor for state 0 on this one. So you're going to be doing this level. So you're calculating the Boltzmann factor for this level. Ashley, can you do this one? So you're doing the Boltzmann factor for this one. It has a degeneracy of 3. All right. And I'll do this last one here so that you can see. So I'm going to calculate this one on the board. And we're doing this at room temperature. So this is the one that I'm doing. Okay. And it's that bottom right hand one. Okay. So I have a degeneracy of 5 actually. Yeah. So let me erase that. Okay. I've got all the numbers on a little cheat sheet here. It's a unitless number. The degeneracy is a unitless number, and all the units in my exponent cancel. If you weren't one of the volunteers, just pick one of these and do them. And so, let's see. What was your number?
Should be
1, okay. Who was the number, the second one? Okay.
I got 0.617.
Okay, good. And then the next one?
I got 0.380.
0.380. Now the nice thing about it is these over here should just be these factors multiplied by their degeneracies, right? So 1 times the degeneracy of 1, so this will be 1.0 as well. And then this one would be 0.617 times 3, so that should be close to 1.85. Is that what you got? Check your work. So that's 1.850. And then this last one should be 1. Oh, I've got, see the numbers are flipped, so it's 0, 1, 2 going down.
Oh.
Okay, yeah. 0.902. These were calculated in Excel, so then the rounding may be different between what you're doing on your calculator. Okay, so then the partition function for the reactants is just the sum of these Boltzmann factors for the reactants. And so we add all of these down, we get 1.997. And so that's our normalization factor for calculating the probabilities. And then the Boltzmann factor for state B, again adding all of these down, it's quite a bit higher, 4.752. That's for those on, yeah, those working on the video, or I'll just go ahead and write this. This was 5 times e to the minus 200 wave numbers over kt. Okay, so they can check their work. All right, so then 1 divided by this is going to be about 0.5. So 0.501. 0.617 divided by 2, essentially 0.309. 0.309. And then 0.38 divided by 2 is 0.190. This is a place now where we can check our work. So these ought to add up to 1. Okay. So 1 and 9 is 10. Carry the 1. 1 and 9 is 10. Carry the 1. So 5, 6, 7, 8, 9, 10. Carry the 1. So it adds up to 1. So that's fantastic. Now let's look at the effect that degeneracy has. So now since we're dividing by something close to 5, this first one has dropped from 50% in the ground state to only 20%, 0.210. So that's 1 divided by 4.752. Okay, the next one's 0.389. And then the last one is 0.400. So this is the highest state, but it's the most populated. That's crazy. Yeah, because it's got a degeneracy of 5.
Yeah.
And so statistically, you throw the molecules in there, and this one has a 40% chance of being populated. And check our work, we should add to 1. Now we've got our partition function, we've got our probabilities, and with the probabilities we can calculate the energy. So we have these equations here, the USHAG equations. And so let's have somebody calculate the internal energy. So it's the energy for each of these 0, 100 wave numbers and 200 wave numbers times our probabilities. 8:48. We're going to be running out of time. Ah, darn. Had too much good discussion. This is, I don't know if this is available. I'll make it available on Blackboard. What I wanted to do, I should have spent more time on it in class, is to calculate all of these for the reactants, all of these for the products, and then we can look at the transitions. So here's where we can see delta U. It's this one minus that one. Yeah. So products minus reactants. So U of B minus U of A is delta U. Whoops. Okay. I'll go ahead and run this down to the bottom, and the equilibrium constant that we're going to get in this case is 2.38. We can get that from delta G. We can also get that from dividing our partition functions. Because remember, this tells us how many states are in the products category, and this is how many states are in the reactants category. So let's just take that 4.752 and divide by 1.997. Can someone do that on their calculator quickly? Yeah, so that's what we get. It's still pretty amazing to me, even though that's, I mean, it should work out, but just going through U and S and H and then getting to G and then doing that equation of the minus of E to the negative delta G over KT, we get 2.38. But you also get the same number from just dividing the partition function. So algebraically, they're the same. I just haven't followed the algebra all the way through all of that. But it is interesting. So you don't have to completely finish the delta G calculation to get to the equilibrium constant. Once you have the partition functions, you can take the ratio and you can get the equilibrium constant. So it's pretty fun stuff. I'll post the answers when I get back to the office so that you can check your work on this long example. I'm tempted to apologize for running over, but we had a good discussion, so I can't apologize for that. I'd rather you be engaged in the class.
I realized it's a mistake. I didn't put a negative sign in the PDF.
Oh, yeah?
I got like 4 points up and I'm like,
Okay, yeah, so that's good to enforce that you got to pay attention to that negative sign.
The last two. I don't remember.
I'm